Right now, like literally as you are listening to this, 41% of all new code being pushed to production worldwide was not written by a human.
Yeah, it's a wild metric.
It's insane. It was written by an AI. So today we're doing a deep dive into exactly how that is happening.
And why it's happening so fast.
Right. Because if you've been feeling overwhelmed by just the sheer volume of noise out there, whether you're a developer, a technical founder, or honestly just someone trying to figure out how to use these AI agents without drowning in all the, theoretical jargon, you are in the exact right place.
Absolutely.
We are going to carve out a really definitive step-by-step path from like total confusion to true mastery, looking entirely at the reality of software engineering right now in the year 2026.
Which is, I mean, it really is a staggering time. That 41% number you just mentioned, that is not an edge case anymore. It's the new baseline.
Yeah.
And that number is climbing every single month. We've officially crossed the threshold from what we used to call the era of syntax into the era of intent.
Okay, I want to focus on that phrase for a second, era of syntax. Because to really understand how massive this shift is, we have to honestly look at what software development actually was for, the last 50 years?
Basically, yeah.
I was thinking about this, and it's essentially like trying to write this sprawling, highly emotional novel, but you're forced to translate it word by word into a foreign language using a massive, totally unforgiving dictionary.
That's a really good way to put it.
Because every single punctuation mark matters. A misplaced semicolon or, a missing curly brace, an indentation error in Python, and the entire book just bursts into flames.
Right, the compiler just yells at you.
Exactly. It's this grueling, friction-filled process of taking human needs like, I just need a button that securely logs the user in, and manually compiling that intent down into abstract machine logic.
And the syntax itself was always the primary barrier to entry. I mean, the human intention, the architectural vision you had, that was always the core value.
Right, the idea was the valuable part.
Exactly.
Yeah.
But the execution required you to be this flawless master of the grammar of the machine. You were essentially acting as a human compiler.
Human compiler, yeah. And now the era of intent completely flips that on its head. It's no longer about you painstakingly using the dictionary. It's like hiring a world-class bilingual ghostwriter.
Yes.
You just provide the vision. You say, hey, I want a scalable architecture that handles thousands of concurrent logins. And the system handles the grammar, the spelling, the syntax. It handles the how, as long as you can rigorously articulate the what.
And if we look at the trajectory of, how we actually arrived here, it explains a lot about why developers are feeling so much whiplash right now.
Oh, for sure.
Because the evolution of autonomy didn't happen overnight, but the acceleration curve was incredibly steep. Think back to, 2021.
Feels like a lifetime ago.
It really does. That was the era of low autonomy. We had simple statistical autocomplete. You type a few characters, and your editor might guess the rest of the variable name.
Right. It was basically glorified spell check. I mean, it was helpful, but it wasn't doing any real thinking.
Precisely. It was just saving you physical keystrokes.
Yeah.
But then, between 2022 and 2023, the context windows expanded. The models got way better at zero-shot reasoning. We got inline suggestions where the model could complete, entire functions just based on a descriptive name.
Which is cool.
Very cool.
Yeah.
And then came chat-based generation. Suddenly, natural language actually became the interface. You could open a sidebar, have a chat with the machine, and it would spit out a working block of code.
Which I remember at the time blew everyone's minds. You could just say, write me a Python script to scrape this specific data table, and boom, there it was. You copy it, paste it into your file, and run it.
It was a massive leap. But structurally, it was still just a reactive tool responding to a direct command.
Right.
It was a single-turn interaction. It relied entirely on you to know what to ask for, and crucially, it relied on you to take the code, test it, find the errors, and figure out what to do next.
You were still the manager.
Yeah. Exactly. But hitting 2024, passing through 2025, and arriving where we are today, the architecture of these systems fundamentally changed. We moved from high capability generation into high autonomy agents.
And this is where I really want to put a pin in it, because this terminology gets abused constantly online.
Oh, endlessly.
The word agent is thrown around by literally every startup with a landing page right now, but there is a very strict technical line drawn in the sources here. What exactly separates a true agent from the chatbot you were using just a couple of years ago?
The critical distinction is continuous self-directed execution.
Okay.
A chatbot is reactive. You prompt it, it replies, and then it goes completely dormant. It has zero agency to advance a goal without your next input.
It's just waiting for you.
Right. An AI agent is a continuous software system. It perceives a high-level goal, and then it operates entirely on its own loop of reasoning and action. It doesn't just generate code and wait for you to run it. It actually takes digital action to achieve the objective on its own.
Okay, let's break down that loop. Because understanding the mechanics here is kind of the foundation of everything else we're going to talk about today.
It really is.
The sources describe it as a 5-step beating heart. Let's make this concrete for the listener. Say I'm a developer, and my intent is to have the agent build a secure login flow for a brand new app. Walk me through exactly what is happening under the hood in those 5 steps.
Okay, let's trace the execution. Step 1 is perceive goal. So in your scenario, the agent ingests your initial prompt, build a secure login flow.
Simple enough.
But perception is more than just reading the text. The agent is analyzing the current state of your code base. It's looking at what framework you're using, like, are you in Next.js? Are you using Django? What database is configured?
Oh, so it's gathering situational awareness.
Exactly. It is pulling in all the context required to understand the reality of the environment it's operating in.
It's taking a snapshot of the world before it makes a move. I love that. What's step 2?
Step 2 is plan steps. This is where the reasoning model is heavily engaged. The agent doesn't just start blindly writing code.
Which is what older models used to do.
Right, and it was a disaster. So instead, it uses its context to break the macro goal down into a micro trajectory. It generates a plan. It thinks, first, I need to create a Postgres migration for the users table with hashed passwords. Second, I need an API route to handle the authentication logic. Third, I need the front-end React components for the UI.
Okay, so it has a sequential roadmap. But honestly, so far, this still sounds like what a really good chatbot could do if you just asked it to think step by step.
And you're right. Step 3 is where the paradigm actually shifts. Step 3 is act, or more technically, tool execution.
Okay.
This is where the agent reaches out of its sandbox and affects the digital world. It doesn't just write the code for the database migration and show it to you in a chat window.
What does it do?
It physically opens a terminal session in the background and runs the command to create the migration file. It uses file system tools to write the React components directly into your directory structure.
Wait, hold on. I need to understand the mechanism there. How does a language model, which is, at its core, just predicting the next token in a sequence of text, actually open a terminal or write a file?
That's the magic of function calling, or tool use. We define strict JSON schemas that represent specific actions.
Like what?
Like a schema for execute terminal command or write to file. The language model isn't actually opening the terminal itself. It is generating a structured JSON payload that essentially says, I want to use the terminal tool, and here's the exact bash script I want to run.
Oh, I see.
And then the orchestration layer around the model intercepts that JSON actually runs the command on the real machine, captures the output, and feeds that output back to the model as text.
That is brilliant. It's like the model is a brain in a jar, and the function calls are the mechanical arms we've wired it to. It sends an electrical signal, the arm moves, and the arm sends back sensory data.
That is a perfect analogy.
Oh.
And that sensory data is exactly what drives step 4. Observe results.
Because the code is never perfect on the first try.
Never. If you are building a complex login flow, maybe the database migration failed because, I don't know, a column name conflicted with a reserved keyword.
Right.
The agent doesn't just halt and ask you for help. It observes. It reads the raw error trace coming back from the terminal tool. It parses the stack trace itself.
And this leads to step 5, which has to be the iterate part.
Yes. Step 5 is iterate. The agent takes that error trace, feeds it back into its own context window, and updates its plan.
Wow.
It reasons, okay, the migration failed because user is a reserved keyword in this specific version of Postgres. I need to rename the table to abusers, update my schema file, and rerun the migration.
So it debugs itself.
Exactly. It then loops back to step 3, acts again, observes the new result, and iterates again. It runs this continuous cycle, sometimes dozens or hundreds of times, until the code compiles, the tests pass, and the feature actually works.
But wait, if it can iterate that fast, what stops it from just going completely off the rails? Like, what if the error is unsolvable? Does it just sit there burning thousands of API tokens, iterating in an infinite loop forever while I get a massive cloud bill at the end of the month?
That is a very real danger. And honestly, it's why raw agents require a massive amount of structure, which we'll get to in a bit. But in a well-designed system, the orchestrator imposes hard limits.
Like circuit breakers.
Exactly. Max iteration depths, token budgets, timeout constraints. If it hits a wall after, say, 10 attempts, it halts the loop and escalates to the human.
Okay, so to recap the loop for you listening, perceive the context, plan the architecture, act via tool calling, observe the actual terminal outputs, and iterate on the failures. That is the engine of the modern AI developer.
And that is the core loop, yes.
But knowing the mechanics of the engine is really only half the battle. Because how a developer chooses to deploy this engine dictates whether they are building enterprise software or just, playing with a very expensive toy.
Right. And that introduces arguably the most important conceptual framework for anyone operating in this space right now. It's the methodology spectrum. You absolutely have to know where you sit on this spectrum for every single project you tackle.
Let's unpack this, because the sources describe two dramatically different ends of the spectrum. On one side, we have something that's been dubbed vibe coding.
Yes, vibe coding.
And I'll be honest, vibe coding sounds incredibly appealing. It sounds fast, it sounds loose, and it sounds like the exact promise of AI we were sold. I just talk, and the computer does the work.
It is the ultimate manifestation of immediate gratification. Vibe coding, which is a term Andres Karpathy popularized back in 2025, is casual, trial and error development driven entirely by natural language.
So no planning.
None. You don't write specs. You don't set up rigid testing environments. You just open your IDE, highlight a blank file, and type, "Build me a dashboard that pulls data from this API and makes it look like a sleek dark mode interface."
And when it breaks, which we know it will.
You don't even really read the code to figure out why it broke.
Yeah.
You literally just copy the massive red stack trace, paste it back into the chat window and say, "Fix this."
That's hilarious.
And the AI apologizes, hallucinates a slightly different approach, and tries again. You are literally just writing the vibes.
Okay, but look, if I'm just building a quick, Python script to parse a messy CSV file for my own personal use, why wouldn't I vibe code it? It genuinely seems like the most efficient use of my time.
Well, for a disposable script, you absolutely should vibe code it. The issue isn't that vibe coding is inherently bad. The issue is its risk profile.
Right.
Vibe coding relies entirely on the AI getting lucky and your subjective visual confirmation that, yeah, it looks like it works. But what happens when that vibe-coded dashboard starts processing real financial data?
Oh, boy.
And it silently drops a decimal point during a race condition that you never even thought to ask the AI to test for?
The vibes instantly turn into a massive liability.
Precisely. Because there is zero formal verification. And that is why, on the complete opposite end of the spectrum, we have what is now known as agentic engineering.
Which is the professional standard.
Exactly. This is what the industry refers to as the factory model of software development.
The factory model. That phrase implies a massive shift in how I actually spend my day. Because if I'm not vibe coding, and I'm definitely not manually typing the syntax anymore, what exactly am I doing in the factory model?
You are no longer the worker on the assembly line turning the wrench. You are the engineer designing the assembly line itself.
Wow.
Your primary job is to build the constraints, define the data pipelines, and most importantly, engineer the verification systems that will check the agent's work autonomously. Agentic engineering has a fundamentally low-risk profile because the verification is systematic and mathematically rigorous.
Okay, this brings up a massive technical distinction that I see people getting confused by constantly online. When we talk about verifying an AI's work in the factory model, we have to talk about tests versus evils.
Yes. Crucial distinction.
Because a lot of developers think, oh, I already write unit tests, so I'm doing agentic engineering. But they are not the same thing at all, are they?
Not even close.
Yeah.
To master agentic engineering, you have to understand the fundamental difference between deterministic code and non-deterministic intelligence. Let's start with standard tests.
Okay.
These are the unit tests, integration tests, and end-to-end tests developers have been writing for decades. They are deterministic.
Meaning they operate on strict binary logic. If I pass the number 2 into this function, it must return the number 4. If it returns 5, the test fails. It's entirely predictable.
Exactly. And AI agents are actually phenomenal at writing standard tests for their own code.
Oh, they love writing boilerplate tests.
They do. You can mandate that every pull request the agent generates must include 100% test coverage, and it will do it. but tests only verify the final compiled output of the code. They do not verify how the agent arrived at that code.
But wait, why does it matter how the agent arrived there, as long as the code works and the test passes?
Because agents are non-deterministic.
Mm.
If you give an agent a complex architectural problem today, it might solve it using one design pattern. If you give it the exact same problem tomorrow, depending on slight variations in token sampling, it might solve it using a completely different, highly inefficient design pattern.
Oh, I see.
The code might still technically pass a unit test, but the methodology was terrible. It might be unscalable or insecure.
Ah, so I need a way to grade the agent's actual reasoning process, not just the output.
Yes, and that is exactly what evals or evaluations are for. Evals check the quality of the agent's trajectory. They evaluate the steps taken, the tools used, and the decisions made along the way.
How does that actually work mechanically? Because I get how to write a Python script that asserts 2 plus 2 is 4. How on earth do I write a script that grades reasoning?
We don't use standard code to grade reasoning. You use another AI model.
Really?
Yeah, you create an eval harness.
Right.
This usually involves a labeled dataset of expected behaviors and a scoring rubric. You take the entire log of everything the agent did, its plan, its tool calls, its iterations, its
The
mistakes.
full chat history, basically.
Right, and you pass that massive log to a separate, highly capable LLM acting as a judge.
So I literally have an AI grading the homework of another AI.
Exactly. You prompt the judge model with something like, review this agent's trajectory. Did the agent explicitly check for SQL injection vulnerabilities during its database planning phase? Did it gracefully handle the API timeout, or did it just crash? Score this trajectory from 1 to 5 based on this strict rubric.
That is fascinating. It's incredibly meta, but it makes total sense. You test the final code to ensure it functions, but you evaluate the agent's trajectory to ensure it is actually following your engineering culture and making sound architectural choices.
And this leads directly to the core philosophy of the 2026 developer.
Yeah.
If you want the agent to make sound choices, you have to feed it the right information. You have to build the environment it operates in.
Which brings us to the secret weapon of modern development: context and harness engineering. I love this topic because it completely shatters a myth that was so pervasive just a couple of years ago. Remember when everyone was selling courses on prompt engineering?
Oh, the LinkedIn hustle was real.
It was everywhere. People were convinced that if you just typed the perfect sequence of magical words like act as a senior distinguished engineer, take a deep breath, and think step by step, the model would suddenly possess superhuman intelligence.
I mean, it was a necessary stepping stone when models were weak and highly susceptible to prompt formatting. But the data today is absolutely definitive. The quality of an autonomous agent's output is not driven by clever phrasing. It is directly, linearly proportional to the quality and structure of its context.
So what does context engineering actually entail? If it's not writing a clever paragraph, what am I actually building?
You are building a localized brain for the agent. Think of it like onboarding a new senior developer to your company.
Okay.
You would just walk up to them on day one, say, build a microservice and walk away. They would fail. Not because they aren't smart, but because they have no context.
Yeah.
They don't know your database schemas, your styling guidelines, or how your CI/CD pipeline works.
Right, you have to give them the company handbook, give them access to the repo, and explain the architecture.
Exactly. And in context engineering, we break this down into 6 structured elements that must be provided to the model. Let's walk through them. Element 1 is instructions.
The basics.
Right. This is the overarching goal, the persona, and the hard operational boundaries. What is it supposed to do, and what is it strictly forbidden from doing?
Okay, element 2 is knowledge.
This is the domain-specific data, the raw architectural diagrams, the API documentation for the third-party services you use, the specific guidelines of the framework version you are running.
Got it. Element 3 is memory.
We touched on this during the loop. Memory is the persistent state. It's the session logs. If the agent is trying to fix a bug, it needs the memory of what it already tried 5 minutes ago so it doesn't just repeat the exact same failing command.
Makes sense. Element 4 is examples.
This leverages few-shot prompting, which is incredibly powerful for agents. If you want the agent to write a specific type of integration test, don't just describe it.
Show it.
Exactly. Provide 3 actual examples of perfectly written integration tests pulled directly from your existing codebase. The agent will pattern match the style flawlessly.
Element 5 is tools, which we know are the defined JSON schemas for external actions like reading files or running terminal commands. And the final element, number 6, is guardrails.
These are safety validations. They're often deterministic rules applied to the context. For instance, instructing the model on the exact format a response must take, or providing rules that block the agent from utilizing certain sensitive data pools.
Okay, so I take these 6 elements, instructions, knowledge, memory, examples, tools, guardrails, and I just dump all of that into the agent's context window.
Oh,
But wait, I can instantly see a massive problem here. If I give the model my entire code base, every architectural diagram, 100 examples, and 50 tool schemas, isn't that just a wall of noise?
yes.
It's like trying to find a specific clause in a 500-page legal contract while someone is shouting a cookbook at you. The attention mechanism of the LLM physically runs out of space to weigh the relevance of the tokens, right?
You've just perfectly described a phenomenon known as context rot.
Context rot.
If you overload the model, the signal-to-noise ratio completely collapses. The model loses focus, begins to hallucinate, or simply ignores the core instruction because it's drowning in irrelevant domain data.
So how do we solve that? How do I give it the context it needs without triggering context rot?
By moving from a static context model to a dynamic context model, you keep the static context very lean, just the core instructions and the immediate goal. For everything else, you build agent skills.
What exactly is an agent skill? Mechanically, how does it work?
An agent skill is a portable package of procedural knowledge and specialized tools that is loaded on demand. Imagine your overarching agent is an orchestrator. It looks at the task and realizes, I need to write an optimized SQL query to fix this migration.
Okay.
Instead of having all the database schemas and SQL rules loaded in its memory at all times, it dynamically loads the SQL database expert skill package.
Oh, it's literally like loading a program in the Matrix. Like, I know Kung Fu, but it only loads Kung Fu when it actually needs to fight.
Exactly. That skill package temporarily injects the specific database schemas, the query optimization rules, and the database connection tools into the active context. The agent performs the task, and then it unloads the skill, freeing up the context window. It keeps the model's attention razor sharp.
That is an incredibly elegant solution. Okay, so we've engineered the context. We've given the reasoning engine the perfect amount of localized data to think clearly. But here is the most shocking revelation from the data we are looking at. The model and the context are just a tiny fraction of the actual system.
This is the reality check for anyone trying to build enterprise AI right now. The equation is simple. Agent equals model plus harness.
Model plus harness.
And in a production environment, the harness constitutes roughly 90% of the actual engineering work.
90%. That's wild. We spend all our time on social media arguing about whether GPT-6 or Claude 4 is smarter, but the underlying intelligence is only 10% of the architecture.
It's true.
Let me use an analogy to ground this. A raw AI model, no matter how massive its parameter count is basically just an engine block sitting on a greasy garage floor.
Right.
It has immense horsepower. It can rev up, make a lot of noise, and burn a lot of fuel, or in this case, tokens. But it is entirely useless. It can't take you to the grocery store.
Because it has no transmission to apply that power to the road. It has no steering wheel to guide it and no brakes to stop it.
Exactly. The harness is the rest of the car. It's the chassis, the axles, the steering column, and the safety systems. Without the harness, you just have a loud, expensive engine. With the harness, you have an autonomous vehicle.
And the data proves this unequivocally. Look at the Terminal Bench 2.0 study from the sources. This was a benchmark designed to test how well agents could solve real-world programming tasks. They took LangChain, a very popular framework, and without changing the underlying LLM at all, they simply optimized the harness around it.
What did they change?
They improved the tool schemas, refined the error parsing, and tightened the sandbox. That's it, just better scaffolding.
And what was the result?
A massive 13.7-point increase in autonomous performance.
Wow.
They didn't make the AI any smarter, they just built a better car around the engine, allowing it to apply its intelligence much more effectively.
Okay, so if I'm listening to this and I want to build a pro harness, what are the concrete physical components I need to be coding? What makes up this 90%?
A production-grade harness consists of 6 core architectural components. First, you need instructions and rule files.
Okay.
The industry standard for this right now is an agents.md file. This lives in the root directory of your repository, right next to your readme.md. It acts as the immutable constitution for any agent entering that code base.
We'll dig into that more later because it's so practical. Component 2 is tools and MCP. I really want to drill into MCP because this acronym is everywhere now. It stands for Model Context Protocol. Explain this to me like I'm a traditional developer who is used to writing custom REST API integrations.
Think of MCP as the universal USB port for AI agents.
Oh, I like that.
Historically, if you wanted your AI to talk to your proprietary database, you had to write custom glue code to map the LLM's output to your database driver. If you wanted it to search Jira, you wrote more custom glue code. It was totally unscalable.
Just endless API wrangling.
Exactly. MCP is an open standard that standardizes how applications expose data and tools to AI models.
So it's a standardized JSON schema protocol.
Exactly. You set up an MCP server for your database. The server exposes a standard list of capabilities. The agent, using an MCP client, connects to it, instantly understands what tools are available, like query table or list schemas, and knows exactly how to format its requests. It makes agents completely plug and play with external resources.
It's a massive time saver. Okay, component 3 is sandboxes.
This is non-negotiable for safety.
Yeah, I'd imagine.
If your agent is writing and executing bash scripts or Python code autonomously, it absolutely cannot do that directly on your host machine or your production service. A sandbox is an isolated, ephemeral environment. It's usually a lockdown Docker container or a micro VM like gvisor.
So if the agent hallucinates a command to delete the entire root directory,
It deletes the virtual file system of an ephemeral container, which immediately spins down and resets. The blast radius is contained entirely within the sandbox.
crucial. You can't let these things run autonomously without that. Component 4 is orchestration logic.
This is the custom routing code that manages the 5-step loop we talked about earlier. It handles the state machine, it decides when to trigger a tool, when to parse an error, and critically, when to spawn a sub-agent.
What do you mean spawn a sub-agent?
If the orchestrator realizes a task is too big, it might spin up 3 smaller agents, delegate parts of the task to them, and then aggregate their results.
Oh, so it manages a team. That's crazy. Component 5, guardrails and hooks. Now, how are these different from the guardrails we put in the context window?
Context guardrails are suggestions to the LLM. You are politely asking the AI not to do something. Harness guardrails are deterministic, hard-coded software hooks. There is no AI involved.
Ah, so it's a physical override.
Exactly. You write a script that intercepts every single API call the agent tries to make. You use regex or AST parsing to scan the payload. If the agent tries to execute a shell command containing RMRF, or if it tries to commit a string that matches the entropy of an AWS secret key, the deterministic hook steps in,
And belongs it.
overrides the model, blocks the execution, and throws a fatal error. It is your emergency brake.
The AI cannot argue with the emergency brake. I love that. And finally, component 6, observability.
You cannot manage what you cannot measure. You need a dedicated dashboard to monitor the agent telemetry. You are logging every prompt, every tool call, the latency of every action, and crucially, the cost of every single token.
Because tokens equal money.
Exactly. You are also monitoring for agent drift, which is when an agent slowly begins to deviate from its core agent.md instructions over thousands of iterations.
Okay, so stepping back. Building this vehicle, a harness with standardized MCP servers, containerized sandboxes, complex orchestration routing, deterministic emergency brakes, and a full telemetry dashboard, it sounds incredibly robust.
It is.
But it also sounds like a massive, really expensive engineering undertaking. Which brings us to the harsh economic reality of this shift. We need to talk about the total cost of ownership, or TCO.
This is the exact conversation happening in every engineering leadership meeting right now, because the economics of software development has completely inverted.
How so?
We used to calculate costs based on developer salaries, server hosting, and software licenses. Now we are operating in the token economy.
The token economy. Right, because every time the agent does anything, every time it perceives, plans, acts, observes, and iterates, it is consuming input and output tokens, and those tokens carry a hard computational cost from the API provider.
Yes. So let's revisit our methodology spectrum, vibe coding versus agentic engineering. But let's look at it purely through the lens of economics. Capital expenditure, or CapEx, which is your upfront investment, versus operational expenditure, or OpEx, which is the ongoing cost to run and maintain the system.
Okay, let's start with the economics of vibe coding. It feels cheap because it's so fast to start.
It does feel cheap. Vibe coding has a radically low CapEx. The data shows it sits around a 12% upfront investment ratio.
Because you don't build anything.
Right. You don't build a harness.
Right.
You don't write evils. You don't configure sandboxes. You literally just pay for a $20 subscription to a chat interface and start typing.
But the OpEx,
Yeah.
The ongoing cost.
The OpEx is astronomical. Because you haven't built any structure or dynamic context routing, you are forced to use the largest, most expensive frontier models for every single trivial task.
Why?
Because only those massive models have the zero-shot reasoning required to operate without a harness. And because there are no automated evils or sandboxes to catch errors early, the agent is going to make mistakes. Constantly.
And what happens when it makes a mistake?
It generates a massive error log. You manually paste that massive error log back into the chat, which consumes thousands of input tokens. The model generates a massive rewrite of the code, consuming thousands of output tokens.
And it probably fails again.
And it fails again. It's a vicious cycle. The sources refer to this as token burn. It is an endless loop of paying premium token prices to ask the AI to fix its own broken, unverified code.
Ouch.
Furthermore, because vibe coding lacks architectural discipline, it creates a massive maintenance tax. A month later, when you need to update that code, no human understands how it works, and you have to burn even more tokens just to map out the spaghetti architecture.
So it's cheap on Monday, but by Friday you are bleeding money.
Exactly. The data reveals a very specific crossover point. After the initial rapid prototyping phase, developing and maintaining a feature through unstructured vibe coding actually costs 3 to 10 times more per feature than if you had engineered it properly.
3 to 10 times more. That is a devastating economic reality for startups trying to move fast.
Huh.
So contrast that with the economics of agentic engineering.
Agentic engineering flips the equation. It demands a high capex. You have to invest significant upfront engineering hours into building the factory. You write the agents.md file, you configure the Docker sandboxes, you write the trajectory evils, and you deploy the MCP servers. That is expensive upfront work.
You are paying expensive engineers to build infrastructure instead of customer-facing features.
Yes. But once the factory is built, your OpEx completely plummets. Agentic engineering results in a highly efficient 12% OpEx ratio over the lifecycle of the project. It's the only mathematically sustainable way to scale AI development in an enterprise.
And a massive part of that OpEx efficiency comes from a technique that I think is absolutely brilliant. Let's talk about intelligent model routing. How does having a structured harness actually allow you to save money on compute?
Well, in an unstructured vibe coding setup, you use a massive, expensive model. Let's call it the genius model for everything.
Right, for every little thing.
With an agentic harness, your orchestrator acts as a traffic cop. It analyzes the specific task it needs to execute in the loop. If the task is design the overarching system architecture for a distributed database, the orchestrator routes that highly complex task to the genius model.
Because it needs deep reasoning, so you pay the premium.
Exactly. But if the next task in the loop is simply take this JSON schema and write a standard Python pydantic model for it, the orchestrator routes that to a much smaller, lightning-fast, incredibly cheap open weights model.
Because the task is highly constrained and requires almost zero reasoning. It's basically just formatting.
Exactly. You might pay 100 times less per token for that specific step. You are only paying for the cognitive horsepower you actually need at any given second.
It's like hiring a master architect at $500 an hour to draw the blueprints, but then using standard, affordable contractors to pour the concrete. You wouldn't pay the master architect to dig a ditch.
Perfect analogy. By routing intelligently, catching errors cheaply in the sandbox, and relying on evils instead of human trial and error, agentic engineering wins the economic marathon, hands down.
Okay, I understand the economics. I buy into the factory model. But this brings up a massive paradox in the data that completely derailed my understanding of this entire transition.
The METR study.
Yes, if I am a developer and my leadership team tells me we are adopting AI agents and building this pro harness so we can all become hyper-efficient 10x developers, I am expecting my daily velocity to skyrocket immediately.
That is the standard expectation, yes.
But the sources cite a major study by METR, which is a leading AI evaluation organization. They studied experienced developers adopting these true agentic workflows. And they found that developers often take 19% longer to complete tasks initially.
Yes, the 19% paradox.
Wait, 19% slower. If I'm doing all this upfront work building evals, tweaking harnesses, writing context files, and my output actually slows down by a fifth, my boss is going to fire me.
You'd think so.
How do I justify this? I thought this technology was supposed to make me instantly faster. This feels like a total failure of the premise.
It feels like a failure only if you fundamentally misunderstand what a software developer is actually doing. To understand the paradox, you have to unpack the cognitive shift happening in a developer's brain.
Break it down for me. Why am I slower?
Let's look at the baseline. Before AI, what did a developer spend the vast majority of their day doing? They were typing syntax. Now, typing syntax is physically slow, but cognitively, for a seasoned engineer, it is a relatively low-stakes, straightforward activity.
Right, right.
You know what design pattern you want, and you just utilize muscle memory to translate that into code.
Right. It's tedious, but it's not mentally exhausting to write a basic boilerplate controller. I can listen to a podcast while I do it.
But when you introduce high autonomy agents, the machine suddenly handles 100% of the typing. The implementation phase drops from 3 days to 45 seconds.
Okay.
So what is the human left doing?
The hard part, the verification, the debugging,
Yeah.
evaluating the architectural trade-off.
Exactly. The human is abruptly shifted from the low-stakes work of generating syntax to the incredibly high-stakes, rigorous work of verifying complex logic and reviewing agent trajectories. It is a known psychological fact that reading, auditing, and verifying complex code is fundamentally harder and slower for the human brain than writing it from scratch.
Wow. Okay, that actually makes total sense. When I write it, I already hold the mental model in my head. I know why every line is there. When I read an agent's code, I have to reverse engineer its mental model to figure out if it missed an edge case.
Precisely. You are suffering from reviewer's fatigue. You are taking 19% longer initially because you have been abruptly promoted.
Or moted to what?
You are no longer the ditch digger laying the bricks. You are the structural building inspector verifying the load-bearing capacity of the walls. Inspecting takes deep, concentrated thought.
So I'm slower on individual tasks at first, not because the tool is bad, but because the tool has elevated me to a much more difficult cognitive tier.
Yes, but here is the critical part. Once you adapt to this new cognitive load, and once your factory, your harness, and your evils is fully calibrated, the total aggregate output of the system vastly outpaces traditional development.
I see.
You might be slower at the micro level of task verification, but you are shipping macro features exponentially faster.
This is a profound realization. This economic and structural shift completely changes what it means to be a software developer on a day-to-day basis. You aren't a typist anymore. You are a technical leader.
And that means the traditional life cycle of software is dead. It has been entirely compressed.
Let's talk about that traditional SDLC. It used to be this massive, slow-moving waterfall or a series of agonizing 2-week agile sprints. You had distinct phases: requirements gathering, design, implementation, QA testing, and maintenance.
And in 2026, those week-long phases have been compressed into iterative loops that take minutes to hours. Let's look at how the developer's role shifts in each phase. Take requirements and design.
Okay.
It used to involve static handoffs. A product manager writes a massive spec doc and hands it to engineering. Now it's an active, real-time conversation. The developer sits with an agent, they talk through the requirements, and the agent instantly scaffolds out a working prototype.
Which means you aren't arguing about where to put a button anymore. You are immediately looking at the working prototype and making high-level architectural trade-offs.
Right. And then we hit the implementation and QA phases, which have essentially merged into one continuous loop driven by the evils we discussed. But I really want to highlight how this changes the final phase. Maintenance.
Oh, yes, the legacy code problem.
Every single company in the world has that one monolithic block of legacy code sitting in the basement of their servers. It's written in an outdated version of Java or COBOL. The original authors left a decade ago, and there is zero documentation.
The do not touch box. Because if you breathe on it, the billing system goes down.
Exactly. Historically, modernizing that code was a nightmare project that no developer wanted. It was too risky. But high-economy agents excel at this exact problem.
Really? Why?
Because they have infinite patience. They can ingest millions of lines of legacy spaghetti code, map out every single dependency, build an internal graph of how the data flows, and then carefully, methodically refactor it into a modern architecture, writing passing tests along the way.
Agents are basically digital archaeologists cleaning up decades of human technical debt. That alone justifies the entire capex of building a harness.
It really does.
Okay, so in this new compressed lifecycle, the sources note that the human developer essentially toggles between two distinct modes of operation. They define them as the conductor and the orchestrator.
These are the two primary hats you will wear, and you need to know when to wear which. Conductor mode is synchronous. It is real-time, highly interactive work.
Okay.
This is when you are still inside your IDE, your code editor. You are watching the code appear, providing fine-grained, line-by-line direction. Stop there, extract that logic into a helper function, rename that variable.
Like a literal orchestra conductor waving the baton, managing the micro-performance of the players in front of them.
Exactly. It's intimate and focused. But orchestrator mode is where the real leverage is realized. This is asynchronous delegation.
How does that work?
You step entirely out of the editor. You define a high-level macro goal for the agent like, migrate this entire authentication database to the new schema and update all API endpoints to match. And then you step away.
You literally leave the keyboard.
You go get coffee. You jump into a design meeting. You work on a completely different project. The agent runs its continuous loop in the background, utilizing its harness and evils. Hours later, you review the final outcome, usually presented as a formal pull request.
So you aren't reviewing individual lines of syntax, you are reviewing the architectural outcome.
Right.
Okay, I hear you. But I have to ask the existential question here. If I'm just orchestrating, if the AI can write the code faster than me, if it can refactor the terrifying legacy systems, and if it can even write its own tests and evaluate its own trajectories in a sandbox, am I obsolete?
A lot of people feel that way.
Seriously, what is the point of the human developer in this ecosystem?
It is the defining anxiety of the era,
Yeah.
but it is unfounded if you understand the limits of machine intelligence. The sources address this directly with a concept called the 80% problem.
The 80% problem. Tell me why I still have a job.
AI is miraculous at racing through the first 80% of any implementation. It will build the boilerplate, the standard API routes, the data models, and the basic UI faster than you can blink. It feels like pure magic because it has absorbed every standard pattern on GitHub.
Right. It knows how to build a login page because there are a million login pages in its training data.
Exactly. But that final 20%, that is where the magic stops. The final 20% consists of the weird edge cases. It is the deeply entrenched architectural debt specific only to your company. It is the subtle, highly nuanced, domain-specific business logic that isn't documented anywhere on the internet.
Because the AI doesn't actually understand your business. It just understands statistical patterns of text.
Precisely. When an agent hits a complex business logic conflict, it doesn't know whether to prioritize data consistency or system availability based on your CEO's goals. It has to know the political context of why a certain feature exists. That final 20% demands deep, nuanced human judgment. The human role isn't gone, it has leveled up.
The bottleneck is no longer how fast I can type the 80%. The bottleneck is how effectively I can navigate and judge the incredibly complex final 20%. I am not a typist, I am a judge. I like that. It feels highly leveraged.
Which leads us to the most practical question. How do you actually start doing this?
Yes. Let's get highly actionable. If a listener is sitting at their desk tomorrow morning looking at a blank project ready to move past the chaos of vibe coding and become a true orchestrator, where exactly do they start? The sources provide a concrete 4-step roadmap for setting up a project the right way in 2026.
And step one is defined by what you do not do. Step one is not start writing code. Do not open a blank Python or JavaScript file and start typing.
Okay, step 1, create your agents.md file. We talked about this as the Constitution earlier. What exactly am I writing in this file?
You are explicitly codifying your static context. You create a simple markdown file in the root of your project. In it, you write out the ground rules. You define your tech stack explicitly. We are using React 18, TypeScript, and Tailwind CSS.
Okay, getting specific.
You define your conventions. All database queries must use the existing ORM, never raw SQL. You establish your hard rules. Never commit API secrets. Always handle errors gracefully. By creating this file, you give the agent an unmoving anchor of truth to rely on, instantly eliminating a massive percentage of potential hallucinations.
It's forcing you to act as a manager before you start the work. I love that. Okay, step 2, initialize the environment. The sources give a very specific command here as an example, UVX, Google Agents Clangware Setup. Now, for the absolute beginner, what is that command physically doing to my computer?
Well, UVX is a modern, ultra-fast Python package runner. When you execute that command, it pulls down a standardized production-ready scaffolding template. It instantly bridges the gap between a messy, local folder and a professional factory model environment.
So it's building the factory floor. What does the floor look like?
It automatically generates the folder structure for your evils. It sets up the configuration files for your Docker sandboxes. It installs the telemetry and observation library so you can track token costs. It wires up the basic harness architecture in a matter of seconds, saving you days of manual configuration.
Amazing. Step 1 is the Constitution. Step 2 is building the factory floor. Step 3, implement protocols, specifically MCP and A2A.
We discussed MCP, the Model Context Protocol. This is where you configure the USB ports. You edit your configuration to explicitly point the agent to your database MCP server or your Jira MCP server, giving it standardized tool access.
And then A2A.
You implement A2A, which stands for Agent-to-Agent Protocol.
Why do I need agents talking to other agents?
Because of orchestration. If your orchestrator agent decides to spawn a front-end specialist agent and a back-end specialist agent to tackle a big feature, they need a standardized language to communicate their state and hand off data to each other.
Oh, that makes sense.
A2A provides that connective tissue, allowing for seamless multi-agent delegation without the data getting mangled in translation.
Okay, the factory is wired up. And finally, step 4. And this one requires a massive paradigm shift for eager developers. Write evils first.
Yes.
True.
We used to have test-driven development. Now we have evil-driven development. Before you allow the agent to write a single line of operational application code, you must define the scoring rubric. You have to write the evil script that will judge the agent's trajectory.
You literally write the test before the code even exists.
Yes, because if you don't mathematically define what success looks like, an autonomous agent will happily run in the completely wrong direction at the speed of light, burning tokens the whole way. Writing the evil first forces the human to deeply understand their own intent.
It's the ultimate check on human laziness. Okay, so that's the 4-step setup. Write the agents.md constitution, run the setup command to scaffold the harness, plug in the MCP and A2A protocols, and write your evils before anything else. But practically speaking, where are developers actually interacting with these agents day to day? Where do they live on my screen?
They exist in 3 main spaces, depending on the mode you are in. First, they live in the editor.
Okay.
Tools like Cursor are dominating this space. This is for conductor mode. You are looking at the code, highlighting a block, hitting a hotkey, and chatting with the agent to refactor a function in line.
It feels like an incredibly smart pair programmer sitting right next to you.
Exactly. Second, they live in the terminal. Tools like Claude Code exist here. This is for broader cross-file work. You aren't looking at specific lines. You are in the command line, asking the agent to search through the entire repository, find a deeply hidden bug, trace it across 5 different files, fix it, and run the build command to verify it worked.
Wow. And third?
They exist entirely in the background. There's pure orchestrator mode. Systems like Google Joules run silently on your infrastructure.
What do they do back there?
They monitor your issue tracker. When a user reports a bug in production, the background agent wakes up, clones the repo, replicates the bug in a sandbox, figures out the fix, writes the test, and submits a pull request for you to review when you arrive at work in the morning.
It is literally having a dedicated team of senior developers working the night shift. It's unbelievable. We have covered an immense amount of ground today, from the friction of manual syntax to the loop of autonomy, the economics of token burn, and the absolute necessity of building a professional harness.
It is a lot to absorb, but mastering this is the reality of the new craft of software engineering.
To crystallize everything we've discussed, the sources distill this entire philosophical shift into 3 core principles. Let's hit them.
Principle number 1, structure scales, vibes don't.
Love that.
Vibe coding is a trap for enterprise software. Discipline, harnesses, and evils are the absolute only way to build production-grade AI systems that actually survive contact with the real world. Stop vibing and start engineering.
Okay, principle number 2. AI amplifies culture.
This is critical for engineering managers. If your team already has strong testing practices, clear documentation, and great communication, AI will multiply those strengths and make your team unstoppable. But if you have sloppy practices, undocumented spaghetti code, and a culture of cutting corners, AI will rapidly multiply that technical debt until your entire system collapses under its own weight. The AI amplifies whatever culture you feed it.
And principle number 3, which is perhaps the most important takeaway for every single person listening. The human role is shifting toward judgment.
The most valuable, highly paid developers going forward are not the fastest typists. They are not the ones who have the syntax memorized.
Or are they?
They are the individuals who can design robust systems, verify complex logic, and judge the output of autonomous agents with absolute precision. Generation is a solved problem. We have machines that can generate anything. Verification, judgment, and direction. That is the new craft.
So what does this all mean for you? If you are listening to this right now, I want you to think back to that blinking cursor we talked about at the very beginning of this deep dive, that blank page. For decades, the fundamental bottleneck to building software was creation. It was the physical and mental friction of getting the code out of your head and translating it into the machine.
Yeah.
But if an AI agent can now generate that code perfectly, execute it in a sandbox, parse the error logs, and iterate on its own in a fraction of a second, the bottleneck is no longer creation.
Not at all.
The bottleneck is you. Are your critical thinking and judgment skills sharp enough to verify what a machine can generate in the blink of an eye? Can you design the factory floor? Next time you sit down to work and you place your hands on the keyboard, I want you to ask yourself a very simple, very defining question. Am I typing or am I judging?
That's the question of the decade.
Thank you so much for taking this deep dive with us today.